Hi, welcome back. So in this video, we are talking about how we use u-Substitution in cases where we have definite integrals rather than indefinite integrals. So specifically, we have to be a little more careful when we evaluate definite integrals using u-Substitution because of the bounds. So indefinite integrals don't have bounds to worry about, but definite integrals do. And we just need to be careful about those bounds when we are doing substitution of variables. Let me show you what this looks like. Let's try an example where we're taking the integral from 1 to 4 of 2x cubed minus 10x quantity squared times 6x squared minus 10 dx. So as this is written, this is an integral with respect to x, and in order to solve this, we are going to perform a u-substitution so that we have an easier integral to solve. So doing this, I noticed that the 2x cubed minus 10x has higher powers on it, so I'm going to use that as my u, since I know that when I take the derivative of u, I'll decrease the exponents by 1, and so I'll be getting the smaller degree item that we have there. So I'm letting u equal 2x cubed minus 10x, and then when I take the derivative of u, I'm getting 6x squared minus 10 dx. So this u-sub is already set up for us. We have the u and the du, so I'm left with an integral of u squared du. Now, the thing to note here is that the bounds are x values on this integral still. So when we started the integral, we were integrating with respect to x, and so that means the bounds are going from x equals 1 to x equals 4. So the bounds are x values, but the integration variable is now u. And we'd really like to just be careful to make sure that we recognize that the variable we're integrating with doesn't match those bounds. Okay, so in order to keep track of the integration variable and the bound variable, we have two options. Really, you can use either of these options, but you'll probably find that one of the options works better for you, and then you can stick to that. So option 1 is that we change the bounds from x to u before we integrate. So whatever the variables were originally, we're going to change the bounds also to u, and then we will evaluate everything using the u bounds. So we write ourselves a new problem where everything is u, we don't have any x's left over anymore. Or the second option is that we leave the bounds as x, or whatever variable it is, it might not be x, but we leave it that way. And at the very end, we have to reverse the substitution and then use the x variable bounds. So we might have to substitute back in for x and get something in terms of x and then evaluate that. So it really depends on which option you like better, and sometimes in certain problems, one option works better than the other one. This is just something that you tend to get more used to the more problems you've done, so I'm going to show you both options just so you sort of get how these work. I also know that in words, they might not mean much, so let's walk through what they look like in practice. So for option 1, we have our bounds currently in terms of x, and what we're going to do is change them to u's. So I like to write these little statements for myself. If x equals 1, then I can substitute in 1 for x, and I know that u is equal to 2 times 1 cubed minus 10 times 1. So that's using what I defined u as. I defined u as 2x cubed minus 10x, and so I can substitute in 1 for x and then evaluate. So I'm getting 2 minus 10 here, and that's negative 8. So I know instead of having x equals 1, I'm going to have u equals negative 8 as that bound. Okay, then for x equals 4, we're going to do the same thing. So we know that u is equal to 2 times 4 cubed minus 10 times 4. So doing that out, I'm getting 2 times 4 cubed is 128, and then 10 times 4 is 40. So I have 128 minus 40, which is 88. So now I can rewrite the integral I had before that had x bounds in terms of u bounds. So my bounds are now negative 8 to 88. U equals negative 8 to u equals 88. And now I just integrate as if this was the problem I was given in the first place. So the antiderivative of u squared is 1/3 u cubed, and I'm evaluating this from u equals negative 8 to u equals 88. So using my fundamental theorem of calculus, I substitute in 88 for u first, and then I subtract off what happens when I substitute in -8. And these are getting to be some gnarly numbers, so I'll write the fractions out here that I calculated separately. I'm getting 681,472 over 3 minus a -512 over 3. And putting those together, I'm getting a minus minus, which is a plus. And so I have 681,984 over 3, which simplifies to 227,328. So I know that's a really big number, but just remember that's finding us an area under the curve between 2 points, so it must just be a really big area. All right, let's try this again with option 2 for our second way to solve this problem, and just keep in mind we should be getting the same answer. So as you're watching through, just look for when we're getting to a point that seems familiar, and you can see where these two options sort of match up at the end. So the second option has us leave the bounds as x and then just reverse the substitution at the end. So let me show you what that looks like. Okay, so I'm going to just write out what our substitution was here, since we're going to need it in a moment and it's now off the screen. So I have u is equal to 2x cubed minus 10x. That's what we did for our substitution. All right, so in this method, we are going to keep the bounds the same and then put everything back in terms of x at the end of the problem. So I just do the antiderivative of u squared. I'm getting 1/3 u cubed, and my bounds are from x equals 1 to x equals 4. All right, so I cannot just put in these bounds yet because they are in terms of x, and my solution is in terms of u. So to simplify, I'm going to replace u with what I initially said it was. So I have 1/3 times the quantity 2x cubed minus 10x all cubed. And this is being evaluated from x equals 1 to x equals 4. So now I plug in 4 for x, and I subtract off what happens when I plug in 1 for x. So doing this, I'm getting something that should start to look a little familiar to what we had before. So I have 1/3 times 128 minus 40 cubed. Then I'm subtracting off what happens when I do 1/3 times 2 minus 10 cubed. And this is getting me 1/3 times 88 cubed minus 1/3 times -8 cubed. And this should look familiar. This is what we had in option 1 when our bounds were -8 and 88. So we're getting to the same process, doing the same math at the end, but this is really just we have to put back in for x before we evaluate those bounds. And we're getting the same answer. So once I plug that in and I compute that, I'm getting 227,328 as my solution. So I kind of see this second option as what you do if you get to the end of the problem, you've taken the antiderivative, and you realize that you forgot to change your bounds. So your bounds are still in terms of x, but your solution's in terms of u, so you just need to put your solution back in for x to get the right variable to use. These methods don't really seem that different because we get to a similar place at the end, but it's just good to know that you can do it both ways because sometimes one might be easier than the other one, and you should know all of your options. Okay, let's do another example. Let's say this time we are doing the integral from 0 to pi over 4 of e to the tangent theta times secant squared d theta. So here we have tangent in the exponent of e, and I'm already thinking to myself that the derivative of tangent is secant squared, so it's going to help me choose my u. So here I'm going to let u be tangent theta, because then when I take the derivative of u, I'm getting secant squared theta d theta. Okay, so this is the substitution we're going to use, and I'm just going to jump right in and try one of the methods first, and then we'll wrap up with the other method for the bounds. So let's do method 1 where we change the bounds at the beginning before we integrate anything. So here I am going to rewrite the integral with my u-Substitution, and I'm just going to remind myself that the bounds are still in terms of theta by writing theta equals 0 and theta equals pi over 4 as my bounds. And then as my integrand, I have e to the u and then du. So we have a new problem where we're integrating with respect to u, and I'd like my bounds to match. So I'm going to write my little statements out so I can determine what the new bounds are. So if theta equals 0, I can substitute in 0 for theta into my u equation, and I'm getting u equals tangent of 0, which you might just know this one, but I'm going to write it out. Tangent is sine over cosine, sine of 0 is 0, cosine of 0 is 1, and so I'm getting 0 as tangent of 0. So my lower bound is now u equals 0. It came from theta equals 0. Then we're going to write a similar statement for the upper bound. So if theta is equal to pi over 4, then we substitute in pi over 4 for theta, and we get that u is equal to tangent of pi over 4, which is sine over cosine. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is the same thing, and so those simplify to be equal to 1. So this means my upper bound is u equals 1, and now I evaluate this integral e to the u du. So I change my bounds first before I do any integrating, and then I don't have to worry about having any x's anymore. I have a new problem now that is written entirely in terms of u, e to the u du with bounds that are u's. So the antiderivative of e to the u is just e to the u. I'm evaluating it from 0 to 1. When I do this, I'm getting e to the 1 minus e to the 0. E to the 0 is just 1, so I have e minus 1. Okay, so that is the solution to this definite integral. Let's try it again with option 2. So remember, option 2 is where we change back to theta at the end before evaluating the bounds. So here I'm just going to go right ahead and integrate even though I have thetas as my bounds. So I'm getting e to the u as my antiderivative of e to the u. Now I'm going to replace u with the substitution. So I have e to the tangent theta, and I'm evaluating this from 0 to pi over 4. So I substitute in pi over 4 for theta. I subtract off what happens when I substitute in 0 for theta. So here I now am back to the original sort of thetas that I started with. I'm not in terms of u anymore, I've gotten back in terms of theta. So I still have to know that tangent of pi over 4 is 1 and that tangent of 0 is 0, but I'm getting e to the 1 minus e to the 0, which is just e minus 1. Okay, so we get the same answer. It's really just a preference, or depending on the problem, which way you're going to use. Just know you really can do it either way, as long as you be really careful about the bounds and what variables they work with. So, just a last note. You should do what helps you be successful. So you might find as you're working on u-substitution that you tend to forget to change your bounds. So maybe you really want to do it early on so you don't accidentally forget. So you're just going to make it a point that you're going to immediately change the bounds as soon as you do a substitution for u, and that's what's going to help you remember. Or maybe you're pretty good about remembering and you're always going to label everything, and you want to do it at the end because it just makes more sense to you that way. You can do whatever you want, whatever works best for you. What is most important is that you keep track of the variables and don't mix them up. So you don't want to get the u variables and whatever variable you started with sort of mixed up and you're accidentally plugging in things for the wrong places. So as long as you keep track of things, you should be good to go, and it's up to you how you make that happen. Alright, that is it for this video. Good luck with your definite integrals. Thanks so much for watching, and I will talk to you in the next one.